AWS Certified Data Engineer Associate. This exam validates skills and knowledge in core data-related AWS services. A data engineering team needs to efficiently migrate large datasets from an on-premises file server to Amazon S3 for analysis while maintaining ongoing synchronization between the two locations. What AWS service can automate this process and ensure data consistency? Option A. Write a program to regularly upload files to S3. This is a custom solution and therefore not the preferred option. Option B. Use AWS Storage Gateway. Now, AWS Storage Gateway is primarily designed for accessing cloud-stored data from on-premises as if it were local. Therefore, it is not the best option. Option C. Use Amazon S3 Transfer Acceleration. This can help with faster upload to S3. However, this is not good for ongoing data synchronization. So, option C is not a good answer here. Option D. Use AWS Data Sync to automate data transfer. AWS Data Sync efficiently migrates large datasets initially and then maintains ongoing synchronization between on-premises and S3, ensuring data consistency. So we will choose option D, AWS Data Sync, as our preferred answer. An analytics team is experiencing slow query performance in Amazon Athena due to a large number of S3 partitions in the dataset, which is managed by AWS Glue Data Catalog. They need to optimize query planning and execution to improve overall query speed. How can they achieve this? So option A, use Athena's partition projection for dynamic partitioning based on common query patterns. This is a good suggestion. Now, Athena's partition projection improves query performance by dynamically selecting relevant partitions based on query filters, reducing data scanned and execution time. Therefore, option A looks like one of the right answers. Option B, merge and create larger S3 objects using AWS Glue jobs. Now, larger S3 objects do not necessarily guarantee better query performance. Therefore, it's likely not the right answer. Option C, make sure all data files are in Apache Parquet format. This is a good suggestion. Apache Parquet format is a columnar storage format and it is going to help with query performance. Therefore, this is likely also the right answer. Option D, delete partitions that are not used. This is an extreme measure and not the right answer. Therefore, option A, using Athena's partition projection, and option C, Apache Parquet format, are the right answers here. A data warehousing team is experiencing performance issues with their Amazon Redshift cluster despite having 4 equally sized nodes. One node is consistently overloaded while the others are underutilized. How can they distribute the workload more evenly across all nodes? Option A, optimize query distribution and performance by modifying the Redshift workload management settings to balance resource utilization across all nodes. Now, this is a reactive approach. It addresses symptoms rather than the root cause. Option B, implement Amazon Redshift's elastic resize feature to dynamically adjust cluster size based on workload fluctuations. This is also a reactive approach and doesn't address the uneven workload distribution problem. Option C, use key distribution on a high cardinality joint column. This is a proactive approach. It targets the root cause by optimizing data distribution. Therefore, is likely the right answer. Let's see option D. Use compound sort key for join columns. Now, this is irrelevant to the problem of uneven workload distribution. Therefore, not the right answer. Therefore, option C, use key distribution on high cardinality join column, is the right answer. It is most effective long-term solution in this specific scenario. Here are some analytics services on AWS. Amazon Redshift is a petabyte scale data warehousing service. Redshift Spectrum Query allows you to run SQL queries from Redshift directly against data stored in S3. Amazon Athena allows you to query data in S3 using SQL. Amazon EMR is a managed Hadoop framework. AWS Glue is an ETL service. Amazon QuickSight is a business intelligence and reporting tool. An e-commerce company stores inventory data in an Amazon Aurora database in a private subnet. They have built a Lambda function to manage this data. How can they ensure that this Lambda function can access the Aurora database securely only through the private network? Option A. Run the Lambda function within the same VPC as the Aurora DB cluster to enable direct communication. This is a good approach because it ensures that the Lambda function can only access the Aurora DB cluster within the private network, preventing unauthorized access from the public internet. Option B. Run the Lambda function in a public subnet and use a NAT gateway to route its traffic to the private Aurora DB cluster. NAT gateways are used to provide internet access to resources in private subnets, not for routing traffic between public and private subnets. Therefore, this is not a meaningful approach. Option C. Configure the Aurora DB cluster's security rules to permit incoming connections from the Lambda function. This is a necessary step to restrict access to the Aurora DB cluster to only the authorized Lambda function. So, this is a good approach. Option D. Enable the private DNS name of the Aurora DB cluster endpoint. While this enables name resolution within the private network, it doesn't address the security or network connectivity concerns. Hence, option A and option C are the right answers here. A data engineer needs to create a simple, fully managed AWS-based system to automate the execution of an AWS Lambda function followed by an AWS Glue ETL job. What is the most efficient way to do this? Option A. Set up AWS batch workflow to execute Lambda function as a job and then execute Glue job. Now, AWS batch is designed for managing and executing large-scale batch computing jobs. While it's powerful for handling heavy compute workloads, it's overkill for a simple sequence of a Lambda function followed by a Glue job. Therefore, option A is not the right answer. Option B. Use AWS step functions to execute Lambda function followed by a Glue job. This is a good option. Step functions are perfect for this. It can orchestrate executing various services in a desired sequence efficiently. Therefore, this is likely the right answer, but let's look at other options. Option C. Use code pipeline to run Lambda function and Glue job in stages. Now, code pipeline is a powerful tool for CI/CD. However, it is not relevant here. So option C is not the right answer. Option D. Configure Amazon Event Bridge to trigger Lambda function followed by a Glue job. Now, Event Bridge primarily focuses on triggering actions based on events. It doesn't inherently provide the ability to define a specific sequence of tasks or handle dependencies between them. Therefore, option D is also not the right answer here. Option B, using AWS step functions, is the right answer. A data engineer is tasked to efficiently integrate third-party datasets into his company's existing analytics platform to improve content recommendations based on user behavior and preferences. How can this be done with minimal operational overhead? So our options are use Amazon Simple Queue service, or use Amazon Kinesis data streams, or AWS Data Exchange, or AWS Data Sync. So option A, Simple Queue service, it is used for message queuing and not for integrating third-party datasets into an analytics platform. Therefore, this will not be the right answer. Option B, Kinesis is ideal for processing and analyzing real-time streaming data, but it isn't specifically designed for acquiring and integrating third-party datasets. Hence, it is not a good option. Option C, AWS Data Exchange, that allows for efficient discovery, subscription, and integration of third-party data directly into AWS services, making it the best choice for integrating datasets with minimal overhead. Therefore, this is likely the best answer. Let's look at option D, which is AWS Data Sync. Data Sync is used for moving data between on-premises storage and AWS, not for integrating third-party datasets into an analytics platform. Therefore, option C, AWS Data Exchange, is the right answer here. A company stores large datasets in CSV format on Amazon S3. They need a solution to directly analyze these CSV files using SQL queries without first moving or converting the data. Which AWS service can fulfill this requirement? Option A, data pipeline to copy data from S3 to RDS for querying. Not a good option because here we are trying to copy data. Option B, Redshift Spectrum to execute SQL queries against CSV data in S3. While this is possible, this requires the use of Redshift, so not a good option. Option C, DMS to load data into RDBMS for querying. Again, we don't want to be loading the data, so not a good option. Option D, Athena to run SQL queries against CSV data in S3. This is the best option. We can use Athena to execute SQL queries directly against data stored in S3. Therefore, option D is the right answer. Your company has large, complex on-premises Oracle database supporting critical business operations. You plan to migrate it to Amazon Aurora Postgres. How would you do this migration to minimize downtime and ensure data integrity? Option A, export Oracle database data as SQL queries and run them against Amazon Aurora Postgres. This method is manual, error-prone, and inefficient. Therefore, not a good option. Option B, use AWS Data Sync to migrate data seamlessly. Now, data sync is used for file-based data transfers, not for migrating databases. Hence, this is not the right answer. Option C, write a script to extract data from Oracle and insert into Amazon Aurora Postgres. Run it during non-peak hours. This approach is complex, requires custom development, and may not handle ongoing replication well. Therefore, this is not a good option. Option D, use AWS Database Migration Service or DMS to migrate data. DMS is designed for database migrations. It supports ongoing replication and ensures data integrity. So this is the best answer here. So option D, AWS DMS is the right answer here. AWS DMS is a service that helps you migrate databases to AWS quickly and securely with minimal downtime. It supports homogeneous, for example, Oracle to Oracle, and heterogeneous, example, Oracle to Aurora Postgres migrations. Continuously replicates data during migration and automatically handles data transformation and schema conversion. How can a data engineer efficiently process and optimize large timestamped CSV files in a S3 bucket for rapid analysis while also separating outdated data on a daily basis using the most cost-effective AWS services? Our options are: run a Lambda function daily to partition and convert CSV data into Parquet format. So here converting to Parquet format is good, but Lambda function is not the best way to partition the data. Option B, use an EMR job to do the partition and conversion to Parquet format. Again, EMR is not the right tool. EMR is good for data processing. Let's look at option C. Use Athena CTAS query to convert data to Parquet format with snappy compression partitioned by date. So since this data is available on a daily basis, partitioning by date is a good idea. Using compression is good here, and Athena CTAS query can do this conversion to Parquet format with snappy compression and partition by date. So overall, option C is good. Option D, Glue job to convert CSV to Parquet format and partition by date. Glue is good for ETL kind of work, so not the right tool here. So option C is the right answer. Here is an example of a CTAS query. CTAS stands for create table as select. In this example, source data is converted to Parquet format and partitioned by a date column. How can a company implement fine-grained access control on data stored in an AWS data lake, allowing specific users to view only designated parts of data sets, rows, and columns, using Athena, Redshift Spectrum, and Hive for querying? Option A, use AWS Lake Formation to set up fine-grained data access policies. This is likely the right answer because AWS Lake Formation can provide this kind of fine-grained access control for the data. Option B, use security groups for data access control. Not the right answer. Security groups are not meant for this kind of access control. Option C, use Amazon Security Hub to define fine-grained access control. Not the right answer. Security Hub is a service that collects security findings from other services, right? So this is not the job of Security Hub. Option C is not the right answer. Option D, use S3 bucket policies for row column level security. Not the right answer. Bucket policies cannot provide row and column level security of data in a data lake. Therefore, option A, using AWS Lake Formation, is the right answer. AWS Lake Formation is a managed service that simplifies the process of creating, securing, and managing data lakes on Amazon S3. It acts as a central control point for governing, securing, and sharing data for analytics and machine learning purposes. What is the relation between lake formation and data lake? AWS Lake Formation is a managed service that sits on top of a data lake and provides a framework for managing, securing, and governing the data in a data lake. It's the control center of your data lake. How can a data engineering team efficiently submit and manage SQL queries against the Amazon Redshift cluster from multiple applications without handling database connections themselves? Option A, use a glue job to query Redshift using necessary drivers. Not the right answer here, because we do not want to use drivers or connections. Option B, use Amazon Redshift data APIs to execute queries. This is a good option and likely the right answer, because Redshift data APIs are straightforward to use. No need to manage any connections or drivers. Okay, so option C, use Redshift Spectrum queries. Not good. We want to query Redshift from other applications. Redshift Spectrum queries instead are initiated from within Redshift. So option C is not the right answer. Option D, utilize Athena to execute queries. Now Athena is primarily meant to query data in S3, and if we are using Athena federated queries, it can query other data sources. However, this is a roundabout complex approach. Option B, use Amazon Redshift data APIs, is the right answer here. Let's go over some database services available on AWS. Amazon RDS is a managed relational database service. Amazon Aurora is a globally scalable high-performance RDBMS which supports multi-region read replicas. Amazon DynamoDB is a fully managed NoSQL database. Amazon Redshift is a data warehousing service. Amazon DocumentDB is a MongoDB compatible fully managed document database. Amazon Neptune is a fully managed graph database service. Amazon TimeStream is a time series database, and Amazon QLDB is a fully managed ledger database. A company utilizes Amazon EMR and Athena for data processing and querying respectively. They need a centralized repository to manage table definitions and properties across these platforms and also incorporate metadata from an existing Apache Hive system. What is the most efficient way to achieve this without extensive development? Option A, define and store the metadata as Parquet files in S3. Not a good option. Option B, use AWS Lake Formation as centralized metadata repository. Not the right answer. Lake Formation is for providing governance to AWS data lakes. Option C, use tables in RDBMS as a metadata store. Not a good option. Option D, use AWS Glue Data Catalog for centralized metadata repository. This is the best answer. Why? AWS Glue Data Catalog is a ready-made AWS service which is meant to solve exactly this problem. All the other options are either completely incorrect or require additional manual work to implement them. Therefore, option D, use AWS Glue Data Catalog, is the right answer. An e-commerce company has historical sales data stored in Parquet format on Amazon S3 and customer data in Amazon Redshift. The data engineering team needs to efficiently join and query both datasets together without loading the S3 data into Redshift. What AWS service or feature can they use to achieve this easily? So option A, Redshift Spectrum Query. This is a good option. Redshift Spectrum Query allows us to query data both in S3 and within Redshift together in a single query by joining them. Therefore, it meets the requirements of this question. Let's look at other options. Option B, export Redshift data to S3 and then query all of it using Athena. While this may work, we don't want to be moving the data around. Option C, use AWS Data Catalog to define metadata for Redshift data. This is irrelevant to the question at hand. Therefore, option C is not the right answer. Option D, use AWS Glue to fetch and process data from S3 and Redshift. Unnecessarily complicated, and therefore we will not be going with option D. So option A, Redshift Spectrum Query, is the right answer here. A service company wants to efficiently consolidate customer interaction data from multiple SaaS platforms into Amazon S3 for subsequent analysis in Amazon Redshift. Which AWS service can automate this data transfer process with minimal operational overhead? Option A, use a glue job to funnel data from SaaS platform to S3. Glue jobs are good at ETL tasks, not really meant for SaaS integrations. Option B, leverage Amazon Airflow to automate this data transfer. Airflow can simplify and automate the transfer of data between SaaS applications and AWS services. It supports integration with a wide range of SaaS platforms and can easily connect to Amazon S3 for data storage. This service offers built-in features for data transformation and scheduling, making it the ideal choice for the scenario. Option C, set up AWS Data Exchange to enable this data transfer. Now, Data Exchange is for buying and selling data products, not for transferring data between SaaS platforms and AWS. Option D, complete data transfer using Snow family of devices. Snow family of devices are for transferring large data sets in an offline manner, which is not necessary in this scenario. Therefore, option B, using Amazon Airflow, is the right answer here. Here's a diagram depicting flow of data from SaaS applications to S3 via Airflow. A team is tasked with managing and querying a dynamic customer transaction dataset stored in Amazon S3. They utilize Amazon Athena for data querying but require an automated solution to adapt to the evolving data structure. Which AWS service can effectively manage the dataset schema and seamlessly integrate with Athena for up-to-date query results? Option A, write a script to continuously monitor S3 bucket for schema changes and notify the team on changes. Option B, maintain the schema definition as a JSON document and refer to it before querying the data. Option C, Glue Data Catalog can be used for schema definition and changes to it. Option D, write a Glue job for continuous data transfer and schema change detection. Of all these options, it is the option C, which uses Glue Data Catalog, that is the right answer, because AWS Glue Data Catalog is a service that is specifically meant for this purpose. It can effectively manage the dynamic schema of your customer transaction dataset and ensure that your queries always return accurate results, even as the data structure evolves. All other options require unnecessary or manual work. Therefore, we should avoid them. Hence, option C is the right answer here. A company stores data in an Amazon Redshift table with an interleaved sort key. Due to frequent data modifications like updates, deletes, the table's performance is declining. How can a data engineer optimize the table for better storage efficiency and query performance while preserving the efficacy of the sort key? Option A, create a new table with a different sort key and migrate the data. This might improve performance for certain queries. It doesn't address the underlying issue and can be time consuming. So not a good option. Option B, increase the number of sort keys in the table. Adding more sort keys can improve performance for specific query patterns, also increase storage overhead and query complexity. Not a good option. Option C, Use Amazon Redshift's compression features to reduce storage size. Compression can improve storage efficiency but may not significantly impact query performance, especially for tables with frequent updates. So, not a good option. Option D. Vacuum the table regularly to reclaim unused space and update statistics. This is the correct answer. Vacuuming removes deleted rows and updates statistics, which can improve query performance and storage efficiency without affecting the sort key. Hence, option D is a right answer. Here are some actions you may perform to optimize and improve the performance of a Redshift database. You may pause the video here to go over this list. How can a data engineer automate the regular ingestion of external stock market data and economic indicators from various external financial dataset providers into their AWS S3 data lake for subsequent analysis? Which AWS service is best suited for this task? Option A. Use Amazon Airflow to fetch and sync data from external data providers into data lake. Airflow is primarily used for integrating SaaS applications like Salesforce, ServiceNow, etc., and not specifically for financial datasets from external providers. Therefore, not the right answer. Option B. Run a scheduled Lambda function to fetch and save data to data lake. Using Lambda requires custom code to handle the data ingestion, error handling, and scaling. It's more manual and less streamlined compared to a service designed specifically for this task. Therefore, it's not a good option. Option C. Configure an AWS Data Exchange to subscribe to financial datasets and import them to data lake. AWS Data Exchange is designed for subscribing to third-party datasets including financial data and automating their import into S3. This makes it the most suitable and automated solution for this scenario. However, we have not yet looked at option D, so let's look at that. Write a Glue job to fetch and save data to data lake. AWS Glue is more suited for ETL tasks once the data is available. Using Glue to fetch external data adds complexity and isn't the primary use case of Glue. Therefore, option C of using AWS Data Exchange is the right answer here. AWS Data Exchange is a service that allows you to securely find, subscribe to, and use third-party data in the cloud. Data providers can publish datasets and subscribers can access the data via APIs or S3. It's useful for integrating external data into analytics, machine learning, or other AWS services without dealing with complex data sharing agreements. A retail company has a large volume of transactional data stored in Amazon S3. To analyze this data using complex queries, they plan to employ Amazon EMR with Apache Hive for batch processing. Given the need to effectively manage and query the complex data structure, which metadata management tool should be integrated into their Amazon EMR environment to ensure seamless interaction with Hive? Option A. Use Glue Data Catalog with EMR Cluster. Option B. Use Amazon RDS as external Hive metastore for EMR Cluster. Option C. Use EMR file system for Hive metadata. Option D. Maintain metadata in a configuration file on S3. Here, clearly, option A, using Glue Data Catalog, is the right answer here, because this is the only service that is specifically designed to be used as a metastore. Other options lack the robust feature set of a Glue Data Catalog or require a lot of custom manual work. Therefore, option A is the right answer here. A data engineer at a retail company is trying to find revenue by each product. However, the query does not fetch products which have never been ordered. And here is the query where we are selecting product ID and doing a sum on order value from the products and orders table, and we join them on product ID and group by product ID. So the question is, how can the query be modified to fetch all products? In other words, products which have never been ordered will not find an entry in the order table. Therefore, those will not be fetched by this query. So how can we modify this query to fetch all products? Option A, add dummy order data to orders table for products with 0 orders. This is not good. We shouldn't be adding dummy data to our tables. Option B, use two separate queries to fetch products with and without orders. So this is doable. We can write another query which will fetch products which have never been ordered and then add those results to the results of the original query. But let's see if there is a better option. Option C, use left join to include products with no orders. Using a left join here is a good and a simple option. This will fetch all products. Option D, add a where condition to select products with 0 orders. Now, it is not clear how you would do such a thing. Therefore, this is also not the right option. So option C, use left join to include products with no orders is the right answer here. A left join is a type of join in SQL that returns all rows from the left table, that is the first table in the join, along with matching rows from the right table, that is the second table in the join. If there is no match, the result will include null for columns from the right table. This ensures that all rows from the left table are included, even if there are no corresponding matches in the right table. And here is the modified query with the left join. Okay, so we have added the keyword left here, and the coalesce keyword has been added to replace the null values with 0. And here is an example of using two separate queries to get the same result. So the first query is the original query that remains unchanged. The second query fetches all products which have never been ordered. Okay, and the results of both the queries are put together using a union clause. How can you design an automated AWS serverless solution that efficiently converts CSV files to Apache Parquet format upon their upload to a designated S3 bucket with minimal effort? Option A, write a Lambda function to check for new files on S3 bucket regularly for conversion to Parquet format. Polling for new files is inefficient and introduces delays and complexity. So not a good option. Option B, configure S3 event notification for put event for files with CSV suffix. Trigger Lambda function for Parquet conversion. Okay, this is efficient and it triggers Lambda function automatically on CSV file upload. Therefore, this is possibly the right answer. Let's look at other options. Use Amazon Event Bridge rule to trigger Lambda function for conversion upon new file upload to S3 bucket. This is less direct than the S3 event notification and better for more complex workflows. Even though this will work, we prefer the previous option, the option B, much simpler and easier to implement. Option D, set up a policy to convert CSV files to Parquet format upon upload. This is not feasible. Policies manage permissions and not data transformations. Therefore, option B is the right answer here. A data engineer needs to schedule daily AWS Glue ETL jobs without strict timing requirements. How should the jobs be configured to minimize costs? Option A, set a long job timeout for the job. This limits job duration, but it doesn't impact cost. So this is not the right answer. Option B, convert the ETL job into Lambda function to save costs. Okay, this is not suitable for complex ETL jobs and costs may not be reduced. Therefore, it's not the right answer. Option C, choose job delay option for Glue job to run job in non-peak hours. Okay, there is no such feature in Glue. There is no job delay feature. Therefore, this is not the right answer. Option D, run AWS Glue job under Flex execution class to use spare compute capacity. Okay, this is a good suggestion. So using spare compute capacity will minimize costs. Therefore, option D is the right answer here. Here's a quick overview of AWS Glue execution classes. Standard, dedicated resources, fast startup, ideal for time-sensitive workloads. Flex uses spare compute capacity, variable start runtimes, cost-effective for non-urgent workloads. A company is looking to upgrade its high-performance cloud storage from Amazon EBS IO1 to IO2 volumes to improve system speed. How can a data engineer seamlessly migrate this storage without interrupting ongoing operations or losing data? Option A, change volume from IO1 to IO2 via AWS Console or CLI without detaching. Option B, use EBS APIs to copy data from IO1 to new provisioned IO2 volumes. Option C, use CLI commands to copy data from IO1 to new provisioned IO2 volumes. Option D, replicate data from IO1 to new provisioned IO2 volumes using data sync. So option A allows for in-place upgrade of the volume type without downtime or data loss. Compared to this, in all other options, you are copying data from one volume to another, which is unnecessary and can lead to disruptions or downtime. So option A, change volume from IO1 to IO2 via AWS Console or CLI without detaching, is the right answer. How can you efficiently extract a specific column from a large Parquet file stored in S3 without downloading the entire file while minimizing data transfer costs? Option A, run a SQL query to extract column data using Amazon Athena. Now, Athena is good with complex queries and can extract specific columns directly from Parquet file in S3. However, let us see if we have simpler options here. So option B, load the file in Hadoop cluster and extract column data. This method involves downloading or moving the file to the Hadoop cluster, which can be costly and inefficient compared to other options. Option C, use S3 Select to extract specific column data. S3 Select allows you to retrieve specific columns from the Parquet file directly from S3, and this is cost effective. Therefore, this is one of the better options here. Let's look at option D. Use Amazon Redshift Spectrum to query column data. Redshift Spectrum queries data directly from S3, but it is typically used for more complex queries involving large data sets, and it may be an overkill for simply extracting a column. Therefore, this is not a good option. Hence, option C, use S3 Select to extract specific column data, is the right answer here. Here is a quick comparison of Athena versus S3 Select. Athena is better suited for complex queries and large-scale data analysis with higher costs but extensive functionality, while S3 Select is a cost-effective solution for extracting specific columns or rows from individual S3 objects with simpler query capabilities. A company needs to automate its data processing workflows and orchestrate complex data pipelines using a managed service. They require a solution that integrates well with various AWS data services and custom scripts, while also allowing them to schedule, monitor, and manage workflows. Which AWS service is best suited for this requirement? Option A, AWS Lambda. Now, Lambda is not designed for orchestrating complex workflows. It is primarily meant for individual functions. So this is not the right answer. Option B, Amazon managed workflows for Apache Airflow. This is ideal for orchestrating complex data workflows and pipelines with AWS data services and custom scripts. Option C, AWS step functions. These are best for coordinating serverless applications and not so much for complex data workflows. Option D, Amazon Kinesis Data Analytics. This focuses on real-time analytics and not on workflow orchestration. Therefore, option B, Amazon Managed Workflows for Apache Airflow, is the right answer here. Here are some orchestration services and their key use cases. Glue for ETL, step functions for workflow orchestration of microservices, Appflow integrating data from SaaS, CRM, etc. Airflow to handle complex workflows. An AWS Glue job is configured to access data from a S3 bucket but fails due to a S3 VPC gateway endpoint issue. Okay, so there is an error. Given that the necessary AWS Glue connection and IAM role are already set up, how can the data engineer establish a successful connection between the AWS Glue job and the S3 bucket? Option A, check the AWS Glue job configuration for correct S3 connection details, including the full address. Now, VPC endpoint issues are unrelated to Glue job configuration details. Therefore, option A does not look like it is the right answer. Let's move on. Option B, check VPC's route table for correct inbound outbound routes for Amazon S3 VPC gateway endpoint. Now, the VPC route table must include a route to the S3 VPC gateway endpoint. If not configured correctly, the Glue job cannot access the S3 bucket. Therefore, this appears to be the right answer. Let's look at option C. Ensure S3 bucket policy has permissions to allow Glue job to access the S3 bucket. Bucket policies don't fix VPC endpoint routing issues. Therefore, option C is not correct. Option D, make the S3 bucket publicly accessible. Making the bucket public is insecure and unrelated to the VPC endpoint issue. Therefore, this is not the right answer either. Hence, option B is the right answer here. A company stores customer data in an Amazon S3 bucket. Analysts from various countries need to access this data for analysis. How can the company restrict data access to only customers within an analyst's country while minimizing administrative overhead? Option A, partition the data by country into separate folders and provide access based on that. Partitioning data by country into separate folders requires managing multiple access policies, increasing administrative overhead. So this is not a good option. Option B, copy customer data of each country to regions closest to that country and provide access to analysts by region. Copying data to different regions increases costs and complexity without directly addressing the access control issue. Therefore, this is not a good option. Option C, implement fine-grained row-level security using AWS Lake Formation to restrict visibility based on analyst's country. AWS Lake Formation allows fine-grained access control, making it ideal for restricting access based on an analyst's country with minimal administrative effort. Therefore, this looks like a good option. Let's look at option D. Load all data into Redshift and create views by country, provide analysts access to their country-specific view. Loading data into Redshift and creating country-specific views adds complexity and cost, which isn't necessary when Lake Formation can handle it more efficiently. Therefore, option C, where we use AWS Lake Formation, is the best answer here. You are tasked with implementing a data mesh architecture for your organization on AWS. Which AWS services would be most beneficial for managing data ownership, governance, and access control across multiple business domains? Option A, AWS Lambda, Glue, and S3. These services are primarily for data processing and storage, not data ownership, governance, or access control. Therefore, not a good option. Option B, AWS Glue Data Catalog, S3, Lake Formation, and IAM. AWS Glue Data Catalog centralizes metadata for data assets making them discoverable and accessible across the organization. S3 is good for data lake storage. AWS Lake Formation focuses on data lake management and governance. AWS IAM provides broader access control capabilities across AWS services. Therefore, this is a good option. Option C, Amazon Athena, Redshift, and Glue. These services are primarily for data querying and analysis, not data ownership or governance. Therefore, not a good option. Option D, Amazon EMR, DynamoDB, Kinesis. These services are more focused on data processing and streaming, not data management or governance. Therefore, option B, AWS Glue Data Catalog, S3 Lake Formation, and IAM is the right answer here. A team of developers maintains a shared Python library used by multiple AWS Lambda functions. Updating the library currently requires manual changes to each function. How can this process be automated to improve efficiency? Option A, store the library path in an environment variable. This is incorrect because it does not address the need to update the library across multiple functions efficiently. Option B, merge all Lambda functions into a single function. This is not practical and doesn't solve the problem of updating the shared library. Option C, store library path in an execution context. The execution context does not manage or update the library code. Therefore, this is not a good option either. Option D, package the library as Lambda layer. Now, Lambda layers allow you to store the shared libraries separately and attach them to multiple functions. So, updating the layer automatically updates all functions that use it. Therefore, this is a good option, and option D of using Lambda layers is the right answer here. A company utilizes Amazon Athena for ad hoc data analysis on data stored in Amazon S3. To accommodate diverse use cases within a single AWS account, the company seeks a solution to enforce granular access control for query execution and query history across different users, teams, and applications. What solution can fulfill these requirements? Option A, for each use case, create an Athena workgroup with tags. Create IAM policy that uses tags to apply permissions to workgroup. Athena workgroups allow you to separate and isolate queries, manage access to query history, and enforce policies. By tagging workgroups and using IAM policies based on tags, you can enforce granular access control across different users, teams, and applications. Therefore, this option looks promising. Let's look at other options. Option B, use Redshift Spectrum instead of Athena for analysis and access control. Redshift Spectrum is an alternative for querying S3 data, but it does not directly address the requirement for granular access control in Athena. Therefore, this is not a good option. Option C, for each use case, create an IAM role with appropriate permissions and assign the role to Athena. IAM roles alone cannot provide the level of granularity needed for controlling query execution and history within Athena. Therefore, this is not a good option. Option D, create separate S3 buckets for each use case and set up bucket policies for access control. Separate S3 buckets help control access to data but do not address access control for query execution and history in Athena. Therefore, option A of using Athena workgroup with tags and IAM policy that uses these tags to apply permissions to workgroup is the right answer. For optimal performance in querying large datasets in Amazon S3 with Amazon Athena and Redshift Spectrum, which format and completion method should you use for the files on S3? Option A, CSV with gzip compression. CSV is row based and not optimized for fast queries. Option B, JSON with snappy compression. Now, JSON is also inefficient for large scale queries. Option C, Parquet with snappy compression. Parquet is a columnar format and good for fast queries, and snappy is a fast compression mechanism. Option D, ORC with gzip compression. ORC is also a columnar format like Parquet and is good for fast queries. However, gzip is slower than snappy for compression and decompression. Therefore, we will go with option C, Parquet with snappy compression. A factory is using Amazon Kinesis to collect and store sensor data for improving efficiency. They want to display real-time efficiency metrics on a large factory screen. Which solution provides the fastest update rate? Option A, use Data Firehose delivery stream to publish data to Redshift. Visualize with QuickSight. Now, Redshift is optimized for complex queries and analytics, not real-time updates. This setup may introduce latency in visualizing data. Therefore, this is not a good option. Option B, use Data Firehose delivery stream to publish data to S3 and visualize with QuickSight. S3 is for long-term storage, not real-time information. Therefore, option B is also not good. Option C, Amazon managed service for Apache Flink to process sensor data and Data Firehose delivery stream to publish data to Amazon RDS and QuickSight for visualization. Now, RDS is not optimized for real-time analytics. This setup may not provide the low latency updates needed for real-time visualization. Therefore, this is not a good option. Option D, Amazon managed service for Apache Flink to process sensor data, Data Firehose delivery stream to publish data to TimeStream-DB, and QuickSight for visualization. TimeStream is optimized for time series data with low latency. QuickSight can visualize this data effectively, providing near real-time updates. Therefore, this is the best answer here. Here are some Kinesis services. Kinesis data streams for real-time data ingestion. Kinesis Data Firehose for data delivery to other services. Kinesis Data Analytics for real-time analytics, fraud detection, anomaly detection, and so on. A company has a large amount of data on premises which must be backed up to AWS Cloud on S3 regularly. The on-premise data changes every day. Which service is best suited for this? Option A, Amazon S3 Transfer Acceleration. Now this speeds up uploads to S3 but does not handle regular backups from on-premises systems. Option B, AWS Data Sync. This efficiently transfers large amounts of data from on-premises to S3 and handles incremental changes, making it ideal for regular backups. Therefore, option B is likely the best answer. Let's look at other options. Option C, AWS Glue Job. Now, glue jobs are used for ETL kind of work, right? Not for data backups. So this is not the right answer. Option D, AWS Transit Gateway. Transit gateways connect VPCs and on-premises networks, and it is not the right service for data transfers or backups. Okay, so option B, AWS Data Sync is the right answer. How can a company automatically scale the read and write capacity of its Amazon Redshift RE3 cluster to meet increased demand? Option A, increase the number of RE3 nodes. This increases storage and compute capacity but does not directly address the need for automatically scaling to meet increased demand. So this is not the right answer. Option B, enable concurrency scaling within workload management at queue level. Now, concurrency scaling automatically adds capacity to handle sudden increases in demand, scaling the read and write capacity efficiently. Therefore, this looks like a good answer. Let's look at option C. Upgrade the RE3 nodes to a higher instance type. This increases performance but does not automatically scale based on demand. So this is not the best answer. Option D. Optimize query performance with query tuning. This improves performance but does not address automatic scaling of capacity. So Option B, enable concurrency scaling within workload management at queue level, is the right answer. You need to implement a daily data pipeline that involves executing a series of long-running Amazon Athena queries given the following AWS services, which would be most cost-effective and efficient for orchestrating these queries. Option A, AWS EMR. Now, this is not correct because EMR is better suited for big data processing using Hadoop, Spark, etc. rather than orchestrating Athena queries. Option B, AWS Glue. Again, this is also not correct because Glue is designed for ETL tasks and might be an overkill for simple query orchestration. Option C, AWS Step Functions. This looks like a good option because step functions can efficiently orchestrate long-running tasks like Athena queries, provide state management and error handling without needing a full-blown data processing platform. Okay. Option D, AWS Lambda. This is obviously not good because Lambda has a max timeout. Okay, and that makes it unsuitable for long-running queries and orchestrating them. So option C, AWS Step Functions, is the right answer. A company is transitioning its high-performance on-premises data processing workloads, which rely on Apache Pig, Oozie, Spark, HBase, and Flink, to handle petabytes of data in seconds, to a serverless AWS environment. The goal is to maintain the same level of performance and scalability while minimizing operational overhead. Which AWS service is best suited for this? Option A, Amazon EMR Serverless. This is a good choice. It is ideal for running open source frameworks like Spark, etc. in a serverless environment. Option B, AWS Glue. No, this is not good because while Glue is an excellent choice for ETL, it doesn't really handle open source frameworks like Spark, HBase, and so on, right? So it's not a good choice. Option C, Amazon Redshift. Again, not a good option. Redshift is primarily for data warehousing tasks. And option D, Lambda, which is obviously wrong because it's good for individual functions, not large scale data processing. So option A, Amazon EMR Serverless, is the right answer here. How can a data engineer effectively deal with data quality issues before loading data into a S3 data lake? Option A, use Lambda function to clean the data while loading it into S3. Now, Lambda functions are not ideal for extensive data cleaning tasks due to their execution time limits and potential complexity. So not the best option. Option B, write a Python script to perform cleanup of data. Now, while this is possible, this approach requires more manual effort and doesn't really leverage AWS's managed services that are designed specifically for data quality management. Option C, use AWS Glue data quality feature in AWS Glue ETL job. Okay. Now, this data quality feature is specifically designed for automating data quality checks and transformations within the ETL process, making it efficient and a scalable way of data cleaning. Therefore, option C is a very good option. Let's look at option D. Import the data in Redshift, use queries to clean the data. This involves unnecessary additional steps and it is not suitable. So option C, use AWS Glue data quality feature in AWS Glue ETL job. That's the right answer. A company wants to improve customer retention by predicting which customers are likely to churn. Which AWS services would be most suitable for building a machine learning model to address this use case? Option A, Amazon SageMaker and Amazon S3. SageMaker provides a comprehensive set of features for building, training, and deploying machine learning models. Amazon S3 is used to store and access the data required for training the model, making this combination ideal for predicting customer churn. So option A looks like a good option. Let's look at option B, Amazon Redshift and Amazon EMR. Redshift is a data warehousing service for analytics and Amazon EMR is used for big data processing. but they do not provide direct machine learning model development and deployment capabilities. So this is not the right answer. Option C, AWS Glue and Amazon RDS. Glue is for ETL tasks and RDS is a relational database service. Neither directly supports building and deploying machine learning models, so this is not the right option. Option D, Amazon Kinesis and DynamoDB. Kinesis is for real-time data streaming and DynamoDB is a NoSQL database. They do not offer machine learning model building capabilities. Therefore, option A, Amazon SageMaker and Amazon S3 is the right answer. A company stores large amounts of log data in Amazon S3. Access patterns show that data is accessed frequently for the first 3 months, then less frequently for next 9 months and rarely thereafter. Which S3 storage class combination would be most cost effective and meet these requirements? Option A, transition data to S3 one zone infrequent access after 3 months and Glacier Deep archive after 9 months. Now, S3 one zone infrequent access is less durable and not suitable for critical data that you want to ensure is not lost even in the case of an availability zone failure. So this is not a good option. Let's look at option B. Transition data to S3 standard infrequent access after 3 months and Glacier Deep archive after 9 months. Now, S3 standard infrequent access provides lower storage costs for infrequent access with high durability. And Glacier Deep Archive is the most cost-effective option for long-term archival storage. Therefore, this is a very good option. Okay, let's look at option C. Transition data to S3 standard infrequent access after 3 months and Glacier Flexible Archive after 9 months. Now, this is more expensive than using Glacier Deep Archive. Therefore, this option is not as good as option B. Okay, let's move on to option D. Transition data to S3 one zone infrequent access after 3 months and Glacier Flexible Archive after 9 months. Now, using S3 one zone infrequent access is not good for any critical data that we cannot afford to lose. So option D is also not good. So we will go with option B. Transition data to S3 standard infrequent access after 3 months and Glacier Deep Archive after 9 months. Option B is the right answer. S3 storage classes. S3 standard, this is the default storage class. S3 intelligent tiering. Here, the data is automatically moved to the most cost-effective storage tier by monitoring access patterns. S3 standard infrequent access. This is for long-lived, less frequently accessed data. S3 one zone infrequent access. Here data is stored in only one availability zone. S3 Glacier instant retrieval. This is for archiving rarely accessed data and it provides quick retrieval. S3 Glacier Deep Archive. This is for archiving rarely accessed data and it provides lowest cost data archiving, and here the retrieval time is in hours. A company maintains a central Redshift data warehouse cluster with customer data and a separate Redshift cluster for the marketing team's analytics. The marketing team requires access to specific customer data from the central warehouse. How can this be achieved quickly and efficiently without compromising the performance of the central data warehouse? Option A. Export the central data warehouse customer data to S3 regularly and import it into the marketing team's cluster. Now, this introduces latency and requires manual updates, impacting performance and data freshness. Therefore, this is not a good option. Option B. Use DMS to migrate data and sync from customer cluster to marketing cluster. Now, this is a complex approach and better suited for continuous migration, not for real-time access. So not a good option. Option C. Export data from both clusters to S3 Data Lake and use Athena to query the data. This adds complexity with data movement and extra querying steps. So not a good option. Option D. Implement Redshift data sharing to securely share relevant customer data from the central cluster with the marketing team's cluster. This provides real-time secure access to data without moving it. and minimizing performance impact. Therefore, option D is a good option and the right answer. How can a data engineer join and query data from DynamoDB, RDS, Redshift, and S3 for one-time analysis in a cost-effective, easy fashion? Option A. Use Amazon EMR serverless to fetch and process data from these sources. EMR is primarily for data processing and not suited for fetching data from multiple different sources. So not a good option. Option B. Query data from all sources using Athena Federated Query. Athena Federated Query allows querying data from S3, DynamoDB, RDS, and so on using a single query interface. Therefore, this is a good option. Let's look at other options. Option C. Export data from DynamoDB, RDS, and Redshift to S3, then query it using Athena. Now, this approach involves data movement and additional steps, which can be less efficient and costlier. So, not a good option. Option D. Write a Glue job to extract and process data from all sources. Glue is more suited for ETL tasks and involves more steps and processing compared to Athena Federated Query. Therefore, we will go with option B. Query data from all sources using Athena Federated Query. A large-scale data processing application requires a highly available and cost-efficient Amazon EMR cluster to run Apache Spark jobs. The cluster must be optimized for long-term operations without compromising performance. Which combination of resources would best meet these requirements? Option A. Use Amazon S3 for persistent storage and Graviton-based instances. So here we have cost-effective and durable storage with S3 and performance-efficient Graviton instances. Therefore, this is a good option. Let's look at option B. Use Amazon EFS for persistent storage and on-demand instances. EFS is more expensive than S3, so not a good option. Option C. Use Amazon DynamoDB for persistent storage and use spot instances. Now, DynamoDB isn't suitable for persistent storage for Spark jobs, right? So this is not a good option. Option D, implement a multi-AZ EMR cluster with instance groups. This does not address the cost efficiency or performance problem stated in the question. Hence, this is not the right answer. So we will go with option A, use Amazon S3 for persistent storage and Graviton-based instances. A company needs to detect anomalies in real-time IoT data and generate alerts. The solution must be capable of advanced real-time anomaly detection, provide low-latency processing, and integrate seamlessly with other AWS services for alerting and data storage. Which AWS architecture is best? Option A, AWS IoT Core and Lambda along with S3 and SNS for alerts. Option B, AWS IoT Core, Kinesis Data Streams, DynamoDB, and SNS for alerts. Option C, AWS IoT Core, Lambda, RDS, and SNS. Option D, AWS IoT Core, Kinesis Data Analytics, Redshift, and SNS for alerts. Now, amongst all these options, only option D uses Kinesis Data Analytics, which can perform advanced real-time anomaly detection. Other options have Lambda or Kinesis data streams and so on, which cannot do this. Therefore, option D, which uses Kinesis Data Analytics, is the right answer. Daily sales data is stored in a S3 bucket and processed by AWS Glue jobs and data loaded into a Redshift data warehouse. Glue job performance is declining. Which two actions would improve Glue job performance? Option A, increase the AWS Glue instance size. Select a more powerful worker type. This is a good suggestion. It will provide more resources to AWS Glue job and therefore it is likely to perform better. Let's move on to other options. Option B, move S3 data to EFS. This doesn't impact Glue job performance in any meaningful way. So not a great option. Option C, increase Redshift cluster size. This does not impact the Glue job's performance. Option D, partition S3 data by year, month, and day. Now, given that this is daily sales data, therefore it is possible to partition this data by year, month, and day, and this reduces the data that needs to be scanned and processed by the Glue job. So this is a good option. Therefore, option A and option D are the right answer here. A data engineer plans to use AWS step functions to process a large collection of data files in parallel, applying the same transformation to each file. Which step function state should be used? Option A, map state. This is used for processing a collection of items in parallel. It allows you to apply the same transformation to each item or file, in this case, in the collection. Therefore, this is likely the right answer. Option B, wait state. This introduces a delay in workflow. It's not suitable for processing files in parallel. Option C, choice state. This is used for branching based on conditions. It doesn't handle parallel processing of items. Option D, parallel state. This allows for parallel execution of multiple branches. However, the map state is more appropriate for processing items in a collection with the same transformation. Therefore, option A, map state, is the right answer. Here are some AWS step function states. Map iterates over an array, executing a task for each element. Wait pauses the workflow for a specified duration or until a condition is met. Choice makes a decision based on conditions or expressions. Parallel executes multiple branches of the workflow in parallel. You have a large dataset of customer records from multiple sources with inconsistent formatting and potential typos in names and addresses. Your goal is to identify and merge duplicate customer records to create a unified customer view. Which AWS Glue transform would be most appropriate for this task? Option A, drop duplicates. This transform only removes exact duplicate records based on a key column, which is not effective for inconsistent formatting and typos. Option B, find matches ML transform. This is a good option because it uses machine learning to identify and merge duplicate records based on similarity data, which is ideal for handling inconsistent formatting and potential typos. Option C, apply mapping. This transform is used to rename and reformat columns, but it does not address duplicate detection or merging. Option D, resolve choice. This is used to handle schema conflicts and resolve ambiguities in data types or columns, but does not focus on duplicate detection or merging. Therefore, option B, find matches ML transform, is the right answer here. A data engineer wants to cost effectively improve Amazon Redshift Spectrum query performance on data stored in Amazon S3. Which two strategies would be best? Split files into smaller files, option A. This may not necessarily improve performance. There will be increased metadata management as well. So this doesn't look like a good option. Option B, import S3 data into DynamoDB and query the same. Now this is costly and inefficient solution as DynamoDB is not optimized for analytical workloads and would incur higher storage and query costs. Option C, for files on S3, use a columnar storage file format. Now columnar format like Parquet are optimized for analytical workloads. So storing data in columns for efficient filtering and aggregation is a good step, and this is likely one of the right options. Option D, partition S3 data by most frequently queried attributes. This is also an effective strategy as it can significantly reduce the amount of data that needs to be scanned for each query. Therefore, option C and D are the right answers here. A company needs to allow an AWS Lambda function to access a private Amazon RDS database securely without exposing the database to the public internet. Which two steps should they take to ensure this while minimizing operational overhead? Option A, configure the Lambda function to run in the same VPC as the RDS database and use private subnets. This ensures that the Lambda function and RDS database are within the same private network, which allows for secure communication. So this is a good answer. Option B, use AWS Systems Manager parameter store to securely store and access the RDS database credentials. Now, while securing credentials is important, it doesn't directly address the network connectivity between the Lambda function and RDS database. Therefore, this is not the right answer. Option C, modify the RDS database security group to allow inbound traffic from the Lambda function security group. This ensures that only the Lambda function can access the database securely. So therefore, this is also a good answer. Option D, enable public access for the RDS database to allow Lambda function access over the internet. Now this exposes it to the internet, which contradicts the requirement for security and privacy. Therefore, option A and option C are the right answers here. A company has multiple applications accessing various subfolders of a S3 bucket. How can we implement access control for these different applications? Option A, move subfolders into separate S3 buckets. This involves reorganizing our data, and we would rather not do it. Let's look at other options. Option B, applications should access S3 bucket only via an access control Lambda function. This adds unnecessary complexity and an extra step in accessing the data in S3. So not a good option. Option C, create separate roles with permissions for each application. Now, while this is feasible, this approach can become slightly complex with increase in number of subfolders and applications. Let's see if we have a better option. Option D, create unique S3 access points with required permissions for each application. This provides fine-grained control and is the most effective solution here. S3 access points are specifically designed for this scenario, offering a streamlined and a secure solution for managing access to shared buckets. Therefore, option D, using S3 access points, is the right answer here. A large dataset has uneven distribution of data. When a distributed computing framework processes it, some processing nodes are underutilized while others are overloaded. What is the term for this data distribution problem? Option A, data shuffling. Data shuffling is redistributing data and it's not about uneven distribution. Therefore, this is not the right answer. Option B, data skimming. This is not a term relevant in this context. Therefore, not the right answer. Option C, data skew. This appears to be the right answer. It refers to uneven data distribution causing load imbalance. And option D is data partitioning. This refers to dividing data based on some criteria, and this does not address the uneven distribution problem being referred to here. Therefore, option C, data skew, is the right answer here. Which data format is best suited for handling data that changes structure over time while ensuring compatibility with older data versions for downstream analytics? Our options are Parquet, JSON, Avro, or XML. Parquet file format is efficient for columnar storage and is not inherently designed for schema evolution. JSON is a flexible format and can handle changing structures, but lacks built-in support for schema evolution and compatibility for it. Avro supports schema evolution with backward and forward compatibility. It is ideal for handling changing structures over time. XML is flexible but lacks efficient schema evolution support and is generally more verbose than Avro. Therefore, option C, Avro, is the right answer. Here are some common data file formats: CSV, text-based; JSON, text-based; Parquet is a columnar format which is efficient for analytics; ORC, a columnar format, provides efficient storage and good compression; Avro is row-based and supports schema evolution. A company policy requires that all data at rest on S3 must be encrypted with encryption keys managed by AWS, but with ability to change the key at any time. Which encryption method meets this requirement? Option A, client-side encryption with customer-managed keys. While this option allows for encryption and key management by the customer, it does not fulfill the requirement that AWS should manage the keys. Option B, server-side encryption with Amazon S3 managed keys. This option uses keys managed by AWS, but the customer cannot rotate or manage these keys. Option C, server-side encryption with customer-provided keys. Again, in this method, the customer fully manages the encryption keys, not AWS. Option D, server-side encryption with AWS key management service. This method meets the requirement by allowing AWS to manage the encryption keys with the ability for the customer to rotate and manage the keys as needed. Therefore, option D, SSE KMS, that is server-side encryption with AWS key management service, is the right answer here. You have millions of images that you need to classify based on their content. Which AWS service can you use to efficiently and reliably classify them? Option A, use Amazon SageMaker to train a machine learning model for this. While you could use SageMaker to train a custom machine learning model for image classification, it requires significant effort in training, tuning, and deployment. Therefore, not the best option. Let's look at other options. Option B, use AWS EMR to process and classify images. Now, EMR is for large-scale data processing. It's not suitable for image classification. Option C, use AWS Glue workflow to read, process, and classify the images. Now, again, Glue is primarily for ETL tasks, and image analysis is not something you would do there. Okay, option D, use Amazon Rekognition to classify the images. Now, Rekognition is a fully managed service that offers image and video analysis capabilities, including object detection, facial analysis, and image classification. Therefore, it is the most efficient and reliable option for classifying large volumes of images based on their content. So, option D, Amazon Rekognition, is the right answer here. You are experiencing intermittent connectivity issues with your Amazon Redshift cluster. After investigation, you suspect a network-related issue. Which of the following is the most likely cause and its potential solution? Option A, incorrect subnet configuration in your VPC. This will cause consistent problems and not intermittent connectivity issue. Therefore, not the right answer. Option B, insufficient Redshift memory allocation. Now, this would cause performance problems and not connectivity problems. So, not the right answer. Option C, security group restrictions preventing Redshift traffic. Again, this would cause consistent connectivity problems and not intermittent. So, not the right answer. Option D, incorrect MTU settings in Redshift cluster. This can indeed cause intermittent connectivity problems due to issues with packet fragmentation. Therefore, option D, incorrect MTU settings, is the right answer here. You have a DynamoDB table storing order information for an e-commerce application. You need to capture changes to order data in real time for downstream processing. Which AWS service would you use to capture these changes? Option A, DynamoDB Streams. This captures real-time changes to DynamoDB tables, and it is purpose-built for such scenarios. Therefore, this is likely the right answer. Option B, Kinesis Data Streams. Now, the Kinesis data streams cannot capture changes to DynamoDB directly. So, option B is not the right answer. Option C, Amazon Redshift. Redshift is a data warehousing service. So, this is clearly not the right answer. Option D, AWS Glue. That's an ETL service, not the right answer. So, option A, DynamoDB Streams, is the right answer here. You have an AWS Glue ETL job processing data from S3 in incremental mode. You want to ensure the job efficiently processes only new or updated data from subsequent runs. Which AWS Glue feature would you leverage to achieve this? Option A, AWS Glue Crawler. Crawler is used to catalog data in AWS Glue Data Catalog. So this is really not the right answer. Option B, AWS Glue Job Bookmarks. This is a feature that can track process data and allows the ETL job to process only new or updated records in incremental mode. Therefore, this is likely the right answer. Option C, AWS Glue Dynamic Frames. These are used for handling schema changes and data transformations, and they do not handle incremental processing of data. Option D, AWS Glue Catalog. This stores metadata about the data sources but does not manage the incremental processing itself. Therefore, option B, AWS Glue Job Bookmarks, is the right answer here. You are experiencing performance issues with an Amazon managed Apache Flink job processing streaming data. The job is experiencing high latency and uneven data distribution across tasks. Which of the following is the most likely cause? Option A, insufficient task manager resources. Now, this can cause high latency but not necessarily uneven data distribution. Option B, insufficient memory allocation. This leads to crashes or maybe out of memory kind of errors and would not typically lead to uneven data distribution. Option C, ineffective key and partitioning strategy for input data. This directly causes uneven data distribution and therefore high latency. Therefore, this is likely the right answer. Option D, network congestion between data source and Flink. This would increase latency but not uneven data distribution. Therefore, option C, ineffective key and partitioning strategy for input data, is the right answer. An Amazon Kinesis application is experiencing throttling errors while consuming data from a Kinesis data stream. Which of the following actions can be taken to improve application performance and prevent throttling? Option A, add more memory and processing power to the application machine. Now, this increases application resources but doesn't solve the throttling problem here, right? So not the right answer. Option B, increase the number of shards in stream and size of get records in application. While more shards can help, but increasing get record size can actually worsen throttling. So not the best option here. Option C, configure enhanced fanout and monitoring on stream. Now, enhanced fanout improves consumer handling but doesn't fix throttling itself. Option D, increase number of shards in stream and add application retry logic for read. So more shards addresses the capacity issues and retry logic handles throttling error. Therefore, option D is the right answer here. You are tasked with setting up a scalable search and analytics solution for a large volume of log data. The requirements are to index and search through this data in near real time and create dashboards for data visualization. Which AWS services should you use to meet these requirements? Option A, Amazon RDS and Grafana. Amazon RDS is not suitable for real-time search of log data. So not the right answer. Option B, Amazon DynamoDB and QuickSight. DynamoDB is not designed again for real-time text search and creating dashboards out of it. So no, not the best answer. Option C, Amazon OpenSearch and OpenSearch dashboards. This clearly is a good choice for indexing log data and doing real-time search on it, and then visualizing this using the OpenSearch dashboards. So this is likely the best answer here, but let's look at option D, Amazon Redshift and QuickSight. Now, Redshift is for data warehousing and analytics, not good for real-time log search. Therefore, that's not the best answer here. So option C, Amazon OpenSearch and OpenSearch dashboards are great for indexing log data and performing real-time search on it. A company is often experiencing performance issues with its AWS Glue ETL job processing JSON and image data. The data engineer suspects that there is a problem with computing capacity for the job sometimes. How can he resolve the problem? Option A, manually adjust DPU count based on historical job performance data. Now, manually adjusting the DPU count can be time consuming and might not react quickly to changing workloads, leading to inconsistent performance. So not a good option. Option B, implement dynamic DPU scaling based on real-time job metrics. So this is a good option. Dynamic scaling adjusts the computing resources automatically based on the job's real-time needs, ensuring optimal performance and cost efficiency. Option C, optimize the AWS Glue script for efficient data processing. While optimizing the script can improve the performance, it does not address the computing capacity issues directly. Option D, increase the timeout duration for the AWS Glue job. Increasing the timeout does not solve the underlying performance issue and only allows the job to run longer. So option B, implement the dynamic DPU scaling based on real-time job metrics is the best answer here. A telecommunications company wants to build a ML model to predict customer churn. The model will utilize customer usage data, demographic information, and customer support interactions. The data engineer is tasked with ensuring data quality, traceability, and efficient model deployment. Which solution best aligns with these requirements? Option A, use Amazon SageMaker Data Wrangler for data preparation and profiling and Amazon S3 for data storage. Amazon SageMaker Data Wrangler aids in data preparation and profiling, while Amazon S3 handles data storage. However, it lacks feature for tracking lineage and managing model deployment. So not a good answer. Option B, implement data quality checks using AWS Glue and store the process data in Amazon Redshift for analysis. This option focuses on data processing and storage and does not cover the full ML workflow or feature storage and tracking which we are interested in. Therefore, option B is not good. Option C, employ AWS Glue Data Brew for data preparation and profiling and use Amazon SageMaker Feature Store for feature storage and lineage tracking. This option covers data preparation and traceability but lacks orchestration for the entire ML workflow. So not the best option here. Option D, utilize Amazon SageMaker pipelines to orchestrate data preparation, feature engineering, model training, and deployment with Amazon SageMaker ML lineage tracking enabled. So SageMaker pipelines orchestrate the entire ML workflow, including data preparation, feature engineering, model training, deployment. SageMaker lineage tracking ensures comprehensive traceability, making it the most complete solution here. Therefore, option D is the right answer here. A company is using SaaS customer relationship management application that stores customer data. The company wants to migrate this customer data to an Amazon Redshift data warehouse for in-depth analytics. Which solution would be most efficient and cost-effective for transferring data from the CRM to Amazon Redshift on a daily basis? Option A, manually export data from the CRM and load it into Redshift using the AWS command line interface. This is clearly inefficient and error prone, especially for daily transfers. So not a good option. Option B, set up an Amazon S3 bucket as a staging area, export data from the CRM to S3 and then load it into Redshift using copy to Redshift command. Now this is slightly more automated approach but introduces additional steps and potential bottlenecks. So still not a good approach. Option C, use Amazon AppFlow to create a flow that extracts data from the CRM and loads it directly into Redshift. Now, this is an efficient and a cost-effective solution as it provides a fully managed serverless service for data integration. Let's look at option D, build a custom ETL pipeline using AWS Lambda and Amazon Glue to extract, transform, and load data from CRM to Redshift. This is a flexible approach, but it requires significant development and maintenance effort, making it not so cost effective for daily transfers. So option C, using Amazon AppFlow, is the right answer. A media company is building a real-time video processing pipeline on AWS. The pipeline involves capturing, processing, and delivering video content. The company needs high-performance, low-latency storage for intermediate video files. Which AWS storage service would be the best choice for this use case? Option A, Amazon S3. Now this is suitable for long-term data storage but has higher latency and is not optimized for real-time processing. So not a good option. Option B, Amazon EBS. Now, EBS is designed for block storage for EC2 instances and is not as efficient for file sharing and high performance workloads. So not the best approach. Option C, Amazon FSx for Lustre. This is a high performance file system designed for demanding workloads like real-time video processing. It offers low latency, high throughput, parallel access, making it ideal for storing and processing intermediate video files. This is a good option. Option D, Amazon Glacier. Glacier is an archival storage service with very low cost but is not suitable for real-time access. So option C, Amazon FSx for Lustre is the right answer here. You are a data engineer at a company that uses Amazon Redshift for its data warehousing needs. You need to load a large dataset from Amazon S3 into an Amazon Redshift table. The dataset is stored in multiple files and you want to optimize the load process for both speed and efficiency. Which of the following options should you consider to achieve this? Option A, split the dataset into smaller files. Now, this can sometimes improve performance, but this is not guaranteed. So let's look at better options. Option B, use the copy command with the parallel option set to on. This allows Redshift to load data from multiple files simultaneously, which speeds up the loading process. So this is a good option. Option C, compress the dataset files using gzip before loading. Now, compressed files reduce the amount of data transferred over the network, and this can speed up the loading process and also reduce storage costs. So this is a good option. Option D, use the copy command with the comp update option enabled. The comp update option in the copy command is used to automatically update compression encodings for columns if they are not specified. While this can optimize storage and query performance, it does not have a positive impact on the speed of data transfer or loading process. It is not the right answer. Therefore, option B, use the copy command with the parallel option set to on, and option C, compress the dataset files using gzip before loading, are the right answers here. You need to optimize the performance of your Amazon Redshift cluster for complex queries and large datasets. Your cluster is experiencing slow query performance. The data undergoes frequent updates. Which of the following actions should you take to improve query performance? Option A, create appropriate distribution keys and sort keys for your tables. Distribution keys and sort keys help optimize how data is distributed and sorted within your Redshift cluster, minimizing table scans and improving query performance. Therefore, this is a good option. Option B, set up Amazon CloudWatch alarms for your Redshift cluster's CPU utilization. Monitoring CPU utilization helps you detect performance issues, but it doesn't directly improve your query performance. So this is not a good option. Option C, export all data to S3 and use Redshift Spectrum query on it. Okay, Redshift Spectrum is useful for querying data in S3 without loading it into Redshift, but exporting all data to S3 is not an optimization for existing Redshift cluster performance. So this is not a good option. Option D, regularly vacuum your Amazon Redshift tables to reclaim space and optimize performance. Vacuuming tables helps remove deleted rows and optimize storage, which can significantly improve query performance. Therefore, this is a good option. Hence, option A and option D are the right answers here. To optimize the performance of your Amazon EMR cluster running Apache Hadoop jobs, you need to optimize overall efficiency and storage costs. Which of the following strategies would you implement to achieve this cost efficiently? Option A, use Amazon EBS volumes for HDFS storage to leverage high IOPS. While EBS volumes offer high IOPS, they can be expensive for massive amounts of data. So not a good option. Option B, enable EMR's automatic scaling to adjust the number of instances based on workload. This strategy allows the cluster to dynamically scale up or down based on the volume of work, ensuring that resources are utilized efficiently and costs are minimized. Therefore, option B is a good option. Option C, store EMR intermediate data in Elastic File System or EFS. EFS is not designed for high throughput and cost efficient requirements of EMR. So this is not the best option here. Option D, configure Hadoop's mapreduce.reduce.memory.mb parameter to allocate more memory to reduce tasks. So by increasing the memory allocated to reduce tasks, you can potentially reduce the number of reduced tasks required, leading to faster job completion and therefore minimize costs. So option B and option D, these are the right answers here.